We now move on from normal shockwaves to oblique shocks. You'll soon see why we've gone through the case of normal shockwaves in such detail. Everything we've learned from normal shockwaves can be applied to our analysis of oblique shocks. Here is a Schlieren image of an oblique shockwave generated by a sharp wedge in a supersonic flow. The flow is from left to right, and the Schlieren imaging shows the shockwave passing up to the right. The wedge causes the flow to deflect upwards. So the flow upstream of the shockwave is travelling in this direction, and the flow downstream of the shock is travelling in a direction parallel to the surface that caused the deflection. Let me just blow this image up in scale so that we can put some velocity vectors on it. So here's our shockwave. Let's just trace the shockwave on this image here. So there's our supposedly straight shockwave. Let's now put our velocity upstream of the shock on the diagram. So there's our velocity upstream of the shock, which we'll call v1. And let's put our velocity downstream of the shock here also. So let's say this is the velocity downstream of the shock, which we'll call v2. So let's keep track of our notation. Let's say that our v1 is going to be greater than the speed of sound because we're interested in a supersonic flow. So it's greater than a1, and we'll call that the upstream flow speed. So the upstream speed. And let's call v2 is going to be our downstream speed. Next, let's put some angles in here. So let's say that the shockwave angle we'll call beta. So that'll be the angle that the shockwave is making relative to the oncoming flow. And let's say that the flow deflection angle, which is the deflection angle of the velocity vector downstream of the shockwave, we'll call that theta. So our beta is going to be the shock angle, and theta is equal to the flow deflection angle. Let me just make a small adjustment here. I'm going to make v1 just a bit longer there so that it's a higher speed than v2 is going to be. Next, we're going to break the velocity into components parallel and normal to the shockwave. So let's start with v1, and let's say that normal to the shockwave is going to be a component of that velocity that we'll call vn1. N for normal and 1 for upstream of the shock. We'll also have a component parallel to the shockwave, so let's draw that in here, and we'll call that vt1. T for tangential to the shock, and again 1 for upstream of the shock. Now straight from the geometry we can say that this angle in here is going to be beta. Now let's put our components downstream of the shock. So the components of v2 downstream of the shock, normal and tangential to the shock. So normal to the shock, there's going to be a component of v2 there, which we'll call vn2, and then parallel to the shock there's going to be the tangential component, and we'll call that vt2. So let's just add that notation to our right hand side. So vn1 is our normal component of the velocity upstream of the shock. vt1 is our tangential component of velocity upstream of the shockwave. And our components downstream, vn2 will be the normal component of the velocity downstream of the shockwave, and vt2 is the tangential component of the velocity downstream of the shock. Now that has set the scene for us. We now have some notation that will allow us to derive some expressions for how properties change across oblique shockwaves. It will also allow us to determine at what angle an oblique shockwave will form for a given flow deflection angle and oncoming Mach number. We move on to those things in the next video.